Today's session, we will discuss how we should handle the radioactive source and then applications of the radioactive isotopes. So if we have a radioactive source in the lab, how we should handle the radioactive source? What are the safety precautions in handling a radioactive source? Number one, because these radiations such as alpha, beta, and gamma, they can damage the skin. They can damage the living cells because they have a greater tendency. Alpha is having the greatest tendency to ionize compared to beta or gamma. But beta and gamma also are harmful or dangerous. Why? Because long-term exposure, if a person or a human or tissues are exposed to these radiation for a longer period of a time, then it will be harmful. So as you can see, we have alpha, beta, and gamma. So alpha, because alpha can cover, like example, 5 to 6 centimeter, even 4 to 5 centimeter in air. So it will be stopped at the top layer of the skin, like on the skin. Where beta, what will happen? It will pass through the tissue. And what is the effect of a gamma? Gamma is highly penetrating, so even it will pass through the human body. So radioactive substance must be handled with a correct procedure to prevent the harmful effect to the people or to the environment. So what are the safety precautions for handling a radioactive material? Number one, we should use a forceps or a tongue to handle the radioactive source, because not directly, we should not hold the this source directly, which you'd use a tongue. So because when you are using a tongue, between you and the source, there is more distance. So that's why it will be relatively safe as compared to directly holding a radioactive source. Then do not point the radioactive source at a living tissue, like the radioactive source should not point toward your face. And we should store the radioactive substance in a lead line box. Why specifically lead line box or a container? Because alpha, beta, and gamma, they cannot pass through lead, or a thick lead will stop these radiation. That's why the box or a container in which we are keeping a radioactive source, it should be have a lead lining so that these harmful radiations cannot come outside and affect the tissues. Then wearing a lab coat, long pants, close to footwear, and gloves when entering a radioactive place. And strong radioactive source should be handled with a robotic control. Because if we use or handle the radioactive source which is very strong, directly a person is exposed, so that will be harmful. So in that case, we should use robotic control to hold the radioactive source. And always check for a surrounding area for a radiation level. So example, to ensure the safety of worker in the lab or laboratories where radioactive sources are used, describe how radioactive material should be stored. So how we should store the radioactive material? So we should store in a box, lead line box. And how we should handle? So we should handle by using a tongs. And wear lead line cloths or suits. So using a tog and wearing a lead line suits and a glove so that we can handle the radioactive source. State 2, social, economic, and environmental issues involved in a storage of a radioactive material with a very long half-life. Like If a radioactive material is having a very long half-life, it remains radioactive for too much time, then what is the social issue? What is in terms of cost? And what might be environmental issue? So in terms of economics, it will be a high cost because we need a material which can store it for a very long time. So it increases the cost to make that material. So it will increases the cost, high cost is there. Then that place where the radioactive source is kept, the material is kept, that place, you don't find, like, tourists won't be allowed. So there will be a reduction in the tourism. That place, visitors cannot come. Then same thing, loss of farming procedure in the land, because we are storing in a lead line box and keeping that for a very long time. So that place cannot be used for a farming. And it will reduction of a land or a property value, because that place where we are keeping a radioactive source, no one will go there. So that will reduce the cost or reduce the price of the land. Then what are the social effects? This was about in financial effects of this radioactive source. Then what are the social effects? Maybe it can cause cancer because long-term exposure, cancer mutation, genetic mutation can be caused. It may, the people might in the place or the animal might become sick. There may, or maybe local objections are there, like people will object that why there is a specific place to keep these sources. And this will also cause a people to switch, like people to go away from that place, because they won't live in a place where there's a radioactive source, as it is having a harmful effect to the health. Then what might be the environmental impact? It might cause a crop mutation, like the plants, the crops which you are growing, that might mutate. That radioactive material might be leakage into a water supply, so that enter to the water supply, and it might pollute to the atmosphere. So these are the environmental impact which this radioactive source will have, which is having a very long half-life. Uses of the radioactive isotopes, where we can use these radioactive isotopes, we can use in radiotherapy. Radiotherapy means for treatment of the cancer. Like example, if a person having a cancer cell is their specific part, so that part only is exposed to the radiation, specifically that part is exposed to radiation, and it can kill the cancer cell. And this we call as a radiotherapy. Radiotherapy refers to for a treatment of cancer. We can also use as a tracer. Tracer means we can use to identify the leakage or the blockage in the pipes. Example, there is a pipeline underground and we want to find the leakage here. So what we will do, from one side we'll inject a radioactive source. So radioactive source will move with the fluid which is moving in the pipe. If any leakage or a blockage is there, like example, if this pipe is having a leakage. So if this pipe is having a leakage at this point, so what happened? Most of the source, as it will leak out or comes out from that point. So we'll detect more radiations, because all the points, the radiations are coming out, but most of the radiations will come out from a point where there's a leakage or the blockage, where that shows that most of the like greater part of a source and is in this region. So to check the leakage of the pipe, what we can do, oil or gas pipelines for a leakage are checked by adding a radioactive isotope to oil or a gas, and the Geiger counter, the GM tube, is moved. The counter does not detect a radiation when the radioactive isotope are in the pipe, but can detect when they are outside. And where the leakage are there, such radioactive source are called tracers. Like example, radiations are coming out from all the points, but the idea is that because most of the leakage is in this region, so most of the sources here, so the counter will record maximum amount of radiation. We can identify the specific point where there is a leakage in the pipe. Can also be used as a thickness gauge. How we can use as a thickness gauge? So we have a radioactive source which is emitting out radiation, and we have a detector. So as the thickness will vary, like example, if the thickness changes, it will get thicker. So the amount of radiation which are passing will change. If it is thinner, few more radiation will pass. But if the sheet is thicker, few radiation will pass. But if the sheet is having a uniform thickness, a constant thickness, so same amount of radiation will pass. So example, say the counter is recording 60 counts, 60 radiations right now. But if the thickness slightly changes, like thickness increases, if there's an increase in the thickness, what will happen? The counts from a detector will decrease. If there's a decrease in the thickness, the counts from the detector will increase. So using the change in the counts, we can identify that the thickness has changed, and we call that as thickness gauge. So when a thin material of a uniform thickness needed, the beta particle are passed through it. So the count raised at the far side of a material is measured, and this then control rollers are there. They can crush the material, and we can identify if there is change in the thickness. As you can see here, if there is a change in thickness, we can identify that the counts will change. As a result, when there's a change in count, we can identify that specific position, the thickness is not same or uniform. Then what is a nuclear fission reaction? The meaning of a nuclear fission. Nuclear fission means when the heavy nucleus break down into a lighter nuclei by the help of a neutron, we call that as nuclear fission. So because and this is a slow neutron, why we are not using electron or proton? Because they are charged, so least likely they will move toward the nucleus. So when we add a neutron, the nucleus become unstable, and that neutron knock out, because it's a heavy nucleus, lot of particles are there. So that neutron knock out the particles, group of particles out into two different nuclei. This reaction is known as nuclear fission reaction. And fission reaction is always a chain reaction. What does it mean, chain reaction? Like we add one neutron, it produces three. And that these three neutrons further collide with uranium, produces more neutrons. So it's like reaction, it's like a chain reaction. The reaction is multiplied, that we start with a one, but like one produces three, then three produces nine, then nine produces 27. So the number of the neutrons multiplied, and the reaction occur for many particles. So we must control this reaction, and how we can control this reaction? By stopping the neutron. And how these neutron can be stopped? We can use a graphite, or which is also known as a control rod, to stop these neutrons. So when a neutron hit the uranium-235, it causes splitting into strontium and xenon. This is the equation. And three more neutrons are there. And what are the uses of nuclear fission reaction? We use this nuclear fission reaction in nuclear power station to generate electricity. So here, by a nuclear fission reaction, it produces heat energy. That heat energy is used to convert the water into steam. And when the steam moves, it rotates the turbine, and turbine will produce. Turbine is connected to generator, which produce electricity. So these are the control rods here. Boron control rods are there. What is the purpose of the control rod? That to control rod remove stop the neutrons from further colliding with the uranium. As a result, the reaction will stop. So nuclear power station, we are using a nuclear fission reaction and normally uranium to produce electricity. So nuclear energy convert into heat or thermal energy, convert to kinetic energy of a water or steam, and then rotated the turbine produces electricity. So these are the energy transformation in nuclear power stations. The second type of reaction, so as you can see, this is a chain reaction. First, the nuclear energy converted in by the nuclear fission, converting to heat energy. Then in a heat exchange, the heat energy is absorbed by the water, converting to steam. Then the steam rotated the turbine, and as a turbine connected to generator, which produce electrical energy. What is a nuclear fusion? When the lighter nuclei join to form the heavy, we call that as a nuclear fusion. As you can see, hydrogen and two isotopes of the hydrogen, they combine and produce helium. Fusion reaction is also exothermic reaction, which release enormous amount of heat energy. That is the main source of the energy. That's how the sun is providing us energy. There's a hydrogen fuel, lot of hydrogen atoms are there, isotopes of the hydrogen. When they combine with each other, as a result, it produces helium and release enormous amount of energy.